Welcome to VolteB University online training. This session covers the architecture of VolteB. This self-paced course introduces you to the major VolteB concepts and architecture. VolteB is an in-memory, partitioned, single-threaded, distributed, ACID-compliant database. In-memory storage provides faster access than disk access used in traditional databases. By being partitioned, VolteB avoids the complexity of manual sharding. By being single-threaded, VolteB eliminates the overhead of locking and latching. By being distributed, VolteB doesn't require rip and replace upgrades. But by being ACID compliant, VolteB provides the same reliability and availability of a traditional database. One of the things that makes VolteB special is in-memory data storage. Designed from the ground up to take advantage of modern computer architectures, VolteB performs all processing in memory, eliminating the delays and contention associated with traditional disk-based systems. Durability features such as snapshots, command logging, and database replication ensure your data is never lost due to system failure. Another aspect of VolteB that makes it special is that it is partitioned. Throughput is maximized by partitioning both the data and the transactions that access that data, so multiple transactions can be processed in parallel. Throughput is easily scaled by increasing either the number of partitions per node or the number of nodes in the cluster. Another way that VolteB is special is that it uses single-threaded transaction execution. Each partition is single-threaded, running transactions to completion. Since there is no contention within the thread, VolteB eliminates the need for locking and latching of database records and much of the associated management overhead that consumes traditional databases. Another way VolteB is special is that it is distributed. Distributing the partitions over a cluster allows VolteB to easily scale both for performance, by having more partitions for parallel execution, and volume, by adding additional memory capacity. Clustering also provides durability and availability. K-safety replicates partitions within a cluster, protecting the database against individual node failures. Database replication creates a duplicate copy of the entire database, providing disaster recovery and allowing for offloading of read-only workloads. VolteB is a fully ACID-compliant database. Unlike NoSQL solutions, VolteB provides the necessary performance without sacrificing the reliability and integrity of a fully transactional database system. Standard SQL syntax for both schema definition using DDL and queries makes programming VolteB applications easy. Simple SQL queries or more complex Java-based stored procedures provide the transactional units that succeed or roll back as required for reliable online transaction processing. In VolteB, the database schema defines both the structure of the data and the transactions that access it. VolteB supports data definition language, or DDL statements, to define not only the data schema, but stored procedures as well. The DDL also lets you define the logical partitioning of both the data and the procedures. At runtime, VolteB partitions the data and the work based on the cluster's physical configuration and the schema's logical structure. Now that we've covered some of the things that make VolteB special, we'll discuss the VolteB architecture, including the database schema, partitioning, clusters, and availability. At the heart of every VolteB database is the schema, which defines the stored procedures, partitioning information, and tables, views, indexes, and other database objects. The schema specifies the logical partitioning of tables and stored procedures. The deployment file specifies how many partitions are created on each node. Once the database starts, you can enter the SQL DDL commands for creating tables, creating indexes, and creating materialized views. The schema also includes stored procedure code and definitions. First, you load the Java classes into the database using the load classes command. Then you use the create procedure from class command to assign the Java class as a stored procedure. Finally, information about the logical partitioning of the data and the stored procedures is included. Using the partition table command to partition a table by one of its columns, and the partition procedure command to partition a procedure by one of its input parameters. Once the database is running, applications connect to the cluster and run stored procedures or ad hoc queries through one of several VolteB client interfaces. VolteB works by partitioning tables across the cluster based on the values of a user-defined column. VolteB also partitions the work, that is the stored procedures, based on the same column value. Because the partitions are independent, multiple queries can be run in parallel. Not all procedures must be partitioned. For multi-partition queries, the partitions coordinate execution. However, too many multi-part queries will impact throughput. Similarly, not all tables must be partitioned. Small, mostly read-only tables can be replicated. This allows more queries to be partitioned, since the replicated table is available from any partition. Here are some best practices for partitioning in VolteB. Design the schema to maximize the use of single partition queries. Use replicated tables for small, primarily read-only data that can serve as lookup tables. VolteB can have multiple partitions on a single server controlled by the sites per host setting. A site is a single-threaded SQL execution engine that stores data and executes SQL statements for one partition. The sites per host setting allows VolteB to be tuned for optimal performance depending on the number of cores available on the server. Deploying multiple servers in a cluster will multiply the number of sites, allowing VolteB to scale out to store more data and run at higher rates of throughput. You can also use multiple servers to replicate partitions to increase availability. Replicating partitions is known as K-safety. With K-safety, one partition runs on multiple sites for redundancy. The K-safety factor indicates how many server failures the database can withstand. The higher the K-safety factor, the more copies exist, the more resilient the database, but also the fewer partitions. When the K factor is set to 0, there will be only one copy of each partition, so the total number of partitions is equal to the total number of sites. And with no redundancy, the cluster can tolerate the loss of 0 servers. When the K factor is set to 1, there will be 2 copies of each partition, so depending on the total number of sites, there will be half as many partitions. But if any one server were to fail, the cluster has at least one copy of each partition and can continue. When the K factor is set to 2, there will be 3 copies of each partition, so there will be 1/3 as many partitions as the total number of sites. In this case, any 2 servers could fail, The remaining server has a complete copy of all of the partitions and can continue. Here are some best practices for setting up a VoltDB cluster. Remember that cluster configuration is a trade-off between performance, achieved by having more partitions, and availability, which is achieved by having more copies of the partitions. It is important to size and configure the cluster appropriately to achieve data size, throughput, and availability requirements. When using K-safety, it is best to use an odd number of servers and to enable network partition detection to protect the database against both hardware failures and network issues. In conclusion, VoltDB is an in-memory, partitioned, distributed, ACID-compliant database. At the heart of a VoltDB database is the schema, which defines the logical structure of the data, the stored procedures, and partitioning information. Partitioning maximizes throughput by performing transactions in parallel. Clusters let you increase performance by increasing the number of partitions and/or increase availability by replicating partitions. You have reached the end of this training session. Additional training lessons provide further information about building database applications.